In order to describe an object's motion, we first must be able to describe its position. Position is simply where an object is at any particular point in time. To do this properly, we must first establish a frame of reference, or origin. This is easier to do if our object relates to stationary objects. For example, a rocket launch can be described in relation to the Earth as a whole. So we can talk about that rocket being 0 meters from the Earth, or sitting on the Earth. We can then talk about it being 100 meters from Earth, and then 500 meters from Earth. What we're doing is we're comparing the position of that rocket with the Earth itself. It is usually convenient to consider motion upward or to the right to be in the positive direction, and motion downward or to the left as a negative direction. This rule, however, is not set in stone, and it is important to pay attention to the coordinate system that is given. Once you define your coordinate system, it cannot be changed. When we describe the position of a professor in the diagram, it would be more convenient to describe it in relation to the edge of the whiteboard. In physics, position is given the notation of x when we are moving in a horizontal direction. When we get in a vertical direction, we'll call it y, but we won't worry about that just yet. At the bottom of your whiteboard is your first physics equation showing how to calculate the change in position. The triangle is the Greek letter delta. In science, we use this symbol to represent a change in a variable. So delta x refers to a change in position. To calculate the change is pretty easy. We simply subtract one position from the other. However, delta is very specific. We must always calculate the final value minus the initial value. So in our example, our professor starts 1.5 meters from the edge of the whiteboard and moves to a position 3.5 meters from the edge of the whiteboard. Her change in position then is 3.5 meters minus 1.5 meters, or positive 2 meters. That positive is important because that tells us what direction she's moving. Since we have defined positive as to the right in this situation, if we say that she has moved a positive 2 meters, that means that she has moved 2 meters to the right. This is important because what happens if she walks back to her original position? She now starts 3.5 meters from the edge and ends 1.5 meters from the edge. So now her delta x is 1.5 meters minus 3.5 meters, or negative 2.0 meters. She has covered the same distance, but in a different direction. So the negative sign in this case means that she just moved to the left instead of the right. There are actually several different ways that you will see this written. X final minus x initial, x2 minus x1, x minus x naught. In this class, we will typically use the xf minus xi, but be aware that it can be written in different ways. Since we have now described a change in our position to the object, we refer to this movement as displacement. Let's look at an example. A cyclist rides 3 kilometers to the west and then turns around and rides 2 kilometers to the east. We want to know what is her displacement and what is the total distance that she travels. Well, our biker is moving directly to the west and then back directly to the east. We can set our frame of reference up to match the center of a compass rose. By convention, we define east, or right of the origin, as our positive direction. So when our cyclist rides west or left with respect to the origin, that is in a negative direction. Whenever she rides back to the east, that is in a positive direction. Displacement was just defined as the final position minus the initial position. Her initial position is at the origin, so 0 kilometers. She rides east and then back west, but her final position is 1 kilometer to the west of the origin. So negative 1 kilometers minus 0 kilometers gives us a displacement of negative 1 kilometers. The value, 1 kilometer, represents the magnitude of her displacement, while the negative represents the direction of her displacement. So this tells us that the displacement was 1 kilometer to the west of the origin. Because we indicated the direction in our description, we refer to this as a vector quantity. Notice that this is not the total distance she traveled on her bike. Initially, she went 3 kilometers west, then she came back 2 kilometers. So her total distance traveled was 5 kilometers. Notice we do not assign a direction to this value. Because distance traveled has a magnitude assigned, but direction is not included, we refer to this as a scalar quantity. So whenever an object is moving, there are two different ways that we can describe a change in position. We can say it has traveled some distance, which is just that, the total distance that it has been covered. In a car, this would be represented by the change in the odometer. Since this total does not include a direction in its description, it is a scalar quantity. We can also describe an object's displacement. This is the difference between the object's ending position and its starting position. This quantity includes the direction from the starting position, so it is a vector quantity.